Okay, let's go ahead and pray. We'll get started today. Father, thank you that you're approachable and that you've opened yourself up through Jesus Christ. We thank you so much for him and that you've given him. We lift up Seth to you today. We ask for healing for his body, that you would be with him, that you would encourage him, and just help him not to fall behind in his studies, but just be an encouragement to him. Thank you for the students that you've given me. I pray that you would help me to explain this new section in a way that's understandable and in a way that would help my students succeed. I give you praise in Jesus' name. Amen.
Amen.
All right. Yes, ma'am.
Do you have a quiz tomorrow?
Yes. Very brief 2-question quiz. It's going to be the last 10 minutes of class. It's going to go over 2 questions. Yep. It's going to give you one thing from 2.4 and one thing from 2.5. Okay?
Just get one wrong.
This is 2.6. This is rational functions. And these puppies are important. So we've got to make sure that we spend just a little bit of time on these. Make sure we get this right. We don't want to get this wrong. Okay? So Joshua, a rational function is a quotient of polynomial functions. It can be written in the form of f of x equals numerator over denominator. You with me? Numerator over denominator. So what we do, Caitlin, is we call the numerator n of x. We call the denominator d of x. And as mathematicians, we want to make absolutely sure that we are never, ever, 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 ever dividing by what?
0.
0. That's exactly right. So whatever d of x is, Abby, we need to make sure that we know where the zeros are, right? So that we don't accidentally plug them in. Okay, which is why we spent so much time in 2.5 learning how to find the zeros of a function. Okay, so we just look at the first example. Here it says find the domain of the reciprocal function f of x equals 1 over x and discuss the behavior of f near any excluded x values. Well, look at the function. What is the numerator function? 1. The denominator function is x. And what are the zeros of the denominator function? 0 itself. So 0 is where we want to avoid. And that right there, Caitlin, is called an excluded x value. So we purposefully exclude the x value. Okay? We exclude 0. Exactly. That's the only point, right? That we can't plug in. Does that make sense? So what we do, Abby, is we go back, we look at the instructions, discuss the behavior of the function near that excluded value. So what we do is we create a table. Here are the x values, here are the y values, and look at what's happening with the x values. -1, -0.5, -0.1, -0.01, -0.001. What is this getting closer to? 0, right? Is it ever going to get there? No. But I want to know what the behavior of the function is, Josh. Yes?
So do you just pick random points, plug in for x? Does it matter?
You want to pick a point, and that can be random at first, but that point needs to approach your excluded value, which in this case, there's only one excluded value. 0.
So you could have started with anything.
I could have started with anything, right, but I want to let it get close to 0.
So you start with something and you go.
And then you step closer and closer and closer to that excluded point that you don't want to actually plug in. And that's how, by the way, Sydney, that is how you discuss the behavior. So this is how you answer the question. Okay? Now what's happening to the y value? Well, the first place it starts off at -1. Now it's -2, -10, -100, -1000. So what's happening to the y value as I approach 0 from the left? It's going down, 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 down towards -infinity, right? And now look at what's going to happen. I graph the function, and look at what happens here. Follow the hand. Going down, 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 down. Going down closer to the y-axis, never will hit it, by the way. But it is going down because I'm approaching 0 from which direction? From the left. And by the way, Abby, direction's important. you've got to be able to approach the excluded value from either the left and the right. And in this case, what's the excluded value again? 0 itself. This is an easy one. This is an easy one, right? Now, look at what happens from the picture. As I approach the excluded value from the right, what's happening to the function? It's exploding to positive infinity. And this right here, Caitlin, is called a vertical asymptote. A vertical asymptote. A vertical asymptote is a vertical line that the function gets closer to and explodes as it gets closer to it. You can have functions that both go up on both sides, by the way. They don't have to be one or the other. Okay, Josh? So this one just happens to be going up on the right and then down on the left.
So you're going to end up with like two parts of it?
You're going to end up with two different behaviors. Two different behaviors. The first behavior is when you approach 0 from the left, the y values do what? When you approach from the left. They go down to negative infinity. And what would the other behavior be? Y goes positively infinite as you approach from the right. So make sure that you're using the word approaching. Approaching. Caitlin, you never actually get there. You're just approaching it, right? You're getting closer and closer. Make sure you use that word, approaching, because that's a key word that, if you don't have calculus with me, if you have it in college or something like that, your college professor will most likely, he or she will use that term, and you need to know what that means. Okay? So far, so good? All right. Now, let's talk about vertical and horizontal asymptotes. In example 1, the behavior of the function near 0 is denoted as follows. This is the kind of notation that I'm looking for, by the way, in your tests and quizzes. This is what I've taught you before, and I'm still looking for this. Using arrow notation, the function is going towards negative infinity as x goes to what? 0. And then, do you see this negative sign here above the 0? This means from the left. That's what that negative sign there means. It means you're approaching 0 from the left. And then right here, do you see the positive sign? That means approaching 0 from the right. Okay? So the function goes to positive infinity as x goes to 0 from the right. So that's what this notation means right here. The line x equals 0 is called a vertical asymptote. From this figure, you can also see that the function has a horizontal asymptote. Check this out. Look at what happens with the curve here. As the hand moves along the curve, what's happening to the y values as x goes to infinity? It's getting closer to what? Which axis? The x-axis. So that's called a horizontal asymptote. It gets closer and closer and closer and closer to that axis, but it will never actually hit it, all right? And that makes perfect sense, Abby, because what happens when you plug in 10,000 into this function? Well, you get 1 over 10,000. And that's a really small number, isn't it? But what happens if you plug in 1,000,000? You get what? It's still not 0, but if you plug in 1,000,000, it's 1 over 1,000,000, and that's even smaller than 1 over 10,000, right? So this is why it's approaching the x-axis. As x does what? As it increases to what? Positive infinity. That's exactly right. Well, what happens as x goes to negative infinity? As it increases to negative infinity. Put in a negative 10,000 here. What do you get? 1 over negative 10,000. Now that's a small number, right? Is it above or below the x-axis? It's below. And Caitlin, that's why this function is always below the x-axis, right here.
That function will never cross either axis.
It will never cross. That's exactly right. It will never cross either axis. What is the definition of a vertical and horizontal asymptote? The line x equals a is a vertical asymptote of the graph of the function if f of x goes to infinity or negative infinity as x goes to a from either the right or the left.
So if the denominator, if the one that excluded is a certain number, that's the vertical asymptote?
That's, you're almost there. Yes and no. The number excluded is going to be a vertical asymptote if the function is exploding to either positive or negative infinity as you approach that excluded value.
Doesn't it always?
No, it doesn't. And I don't know if it'll be in this lesson, but I will show you in a certain lesson coming up that it doesn't always. That it can actually happen where you approach an excluded value, but it's not exploding.
Why doesn't the horizontal asymptote have an f before the x in the beginning?
Why doesn't the horizontal asymptote have a what?
An f before the x.
Because, you mean right here? Because what the function is doing is it's approaching a constant. Now, let's go back to our example. What are the y values approaching here as x goes to infinity? They're approaching 0. 0 is a constant, isn't it? Okay. Now, does the horizontal asymptote always have to be 0? No. We're going to have plenty of examples where the horizontal asymptote is not 0. So the reason why it doesn't have an f here is because the y values are right here, Katie. They're approaching some constant, we'll call it b, as x does what? As x goes to infinity or negative infinity. Okay? So let's look at the following cases. Here's the function f of x equals 2x plus 1 over x plus 1. What is the excluded value here? What is the excluded value? Negative 1, right? Does that make sense? Okay, so we can't let this be negative 1, so what we do, Abby, is we approach negative 1 from the left and from the right. And look what happens. The function, as we approach from the left, what's it doing?
Wait, how would you draw that graph from like what you have?
Excellent question. I'm going to teach you skills to draw it, but right now you're reduced to the calculator.
Okay, so you just plug that in?
Right now you plug it in the calculator. But there are skills to learn how to draw it, and that's something we're going to go over. Okay. But follow the hand. What's happening to the y values as I approach negative 1 from the left? Going towards positive infinity. And that right there, Sydney, is all you need to have a vertical asymptote. You go infinite from one direction. But look what happens here, Abby, as I approach from the left. Follow the hand. What are the y values doing? Going towards negative infinity. So this is a legitimate vertical asymptote. Now, check the horizontal asymptote. Follow the hand again. As x goes to negative infinity, the y values are doing what? Approaching 2. Follow the hand. As x goes to infinity, approaching 2 again. Somebody asked me a question once. They said, Mr. P, do you have to approach... For the horizontal asymptote, do you have to approach the same thing from both sides? And the answer is no. To have a horizontal asymptote, it can only be one side. It doesn't have to be two sides. So as long as you're approaching something from the left and it's going to a constant, Abby, it is a legitimate horizontal asymptote. Okay.
Why is it 2? Does it matter what number it is?
It does matter why it's 2. That's an excellent question again. Let's plug in. What happens if we plug in 1? Well, we have 2 times 1 plus 1, which is 3, over 1 plus 1, which is 2. 3 over 2 is 1.5, right? Now let's plug in something even bigger. 2 times 100 plus 1 over 100 plus 1. Now what happens when you take 201 divided by 101? Not 2, but close to 2, right? Take your calculator real quick. Take 201 and divide it by 101. And then tell me what you get. 1.9999. So is that number close to 2? Yeah. Now plug in 10,000. 2 times 10,000, 20,000 and 1, right? divided by what? 10,001. And what does that give you? Yeah, 1.9999999999999. And that's even closer to 2, isn't it? So what's happening to the function as you approach infinity, as we're getting larger and larger and larger? What's happening to the y value as x is getting larger and larger and larger? It's getting closer to the number 2. That's exactly right. That's an excellent question. Why 2? Here I get 1.999.
Isn't the 2, we got that from like,
You want the closest constant, right?
Say that again?
You want the closest constant.
I want what it's approaching. So it's approaching 2 in this case.
Oh, but it's never going to hit 2.
It's never going to hit 2. You got it. Man, you nailed that. It's never going to hit 2. Right? Now, can you look at the function and tell me why it's going to be 2? It's because of this 2 right here. Okay? Now, you got to be careful because there are some tricks to learn when that works and when that doesn't work. And those are things I'm going to teach you. Okay? Let's look at this function right here. Look at the denominator. Do we have any excluded values for the denominator? Square root of negative 1? That would be I. And I isn't real. It's imaginary. Do we have any real numbers that are excluded values?
No.
We don't. So because of that, Caitlin, there's no place where this function will be 0 in the denominator. So that means that the domain is what? All real numbers.
Well, you said both sides don't have to approach the same asymptote. Is that possible that there could be 2 horizontal asymptotes?
That's an excellent question, and it is possible. Yes, you can have 2 horizontal asymptotes. Yep. So here, look what's happening. This, they're already telling you, plug in, let's plug in 100. 4 over 100 squared plus 1, is that a large number or a small number? Small number. Then 4 over 1,000,000 squared plus 1. Even smaller. So does it make sense that the y values get closer and closer and closer and closer to 0 as x does what?
It's smaller.
No, not x. X is going off to the right. X is getting larger toward, and it's approaching what? Infinity, positive infinity, right? And I'm constantly going to be doing this. I'm going to be saying, okay, x is doing this, what is y doing? Okay? Y is doing this, what is x doing? Okay? So you have to kind of think both ways now. You got to think x's and y's here. Look at this. Here's 2 over x minus 1 squared. What's the excluded point that we can't have? 1. Now we approach 1 from the left, and look what happens. Explodes to positive infinity, right? Approach 1 from the right, explodes again to positive infinity. Let me ask you a question. Why is it going in both directions? Why is it going positive in both directions? Because of the square. What does a square do to a number? Always makes it positive. So if I plug in 0.99, here's 0.99. 0.99 minus 1 is negative 0.01, right? But I have to square that, and that makes it, so this is always going to be 2 divided by a positive number. Does that make sense? So that's why it's exploding to positive infinity from both sides.
Why is the horizontal asymptote 0? Why isn't it 2?
Okay? Sydney's asking, why is the horizontal asymptote 0 and not 2? And the answer to that question is, let's let x get bigger and bigger and bigger and bigger. So let's just start with 100. 2 over 100 minus 1 squared. What's 100 minus 1? 99 squared is something, right? Something big? What's 2 divided by something big? Something small, right? Now let's let x get even bigger. X is 10,000. 10,000 minus 1 is? 9,999. What's 9,999 squared?
Big number.
Something really big, right? What's 2 divided by something really big? Something really small, right?
Zero.
It's almost 0. That's exactly right. That's the answer to your question. That's why it's going to 0 and not 2.
Because it's almost zero.
Right. But now let's go back to the original. Maybe I can teach you a little bit why this is going to 2, the very first one. Because look at the power of x here. What's the power of x? No? 1.
Oh.
What's the power of x here?
1.
Ah. If they're the same... Seth can't see this, so I'm making a funny face. If they're the same power, then chances are pretty good we're going to approach some constant other than
Zero?
0.
Would it be like the leading coefficient like 2?
Oh, you're thinking ahead. Shame on you. Yep, you're right. Okay, this is nasty notation for something very simple. Vertical and horizontal asymptotes of a rational function. Caitlin, we're just viewing a rational function as a numerator function over a denominator function. The numerator, here's the polynomial, and this is just mathematical notation for saying some coefficient times x to the nth power. What is n? Well, it could be 5, right? Could be 4, could be 15. All the way down to plus some constant. So a polynomial over a polynomial, where n and d have no common factors. That means that they have nothing in common for factors, all right, which means you can't divide them nicely. The graph of f has vertical asymptotes wherever the zeros of d, wherever you have zeros of denominator, okay? Which again is why we did all that stuff in 2.5, finding the zeros of a polynomial function. Why do you want to find the zeros of a polynomial function? Because you don't want your rational functions blowing up on you, right? So you have to know where those zeros are. Find those zeros, then you know it won't blow up on you when you're making a calculation, okay? Now, Sydney, in answer to your question before, can it be an excluded value and still not have a vertical asymptote? The answer is yes, and when that happens is when the numerator and denominator have a common factor, which means the factor divides away. That's when it happens. That's called a removable vertical asymptote. But let's not worry about that too much right now, okay? We'll get into all that. Example 2, find all vertical asymptotes, vertical and horizontal asymptotes of the graph of each rational function. Let's just look at part A. What are the excluded value or excluded values of part A?
It's all real numbers. Wait, the 1.
For the bottom, all real numbers. What if I plug in 1?
Oh, yeah.
That's a problem point. So 1 is an excluded value. Is there anything else?
0.
0 squared minus 1, is that 0?
No.
Oh,
No.
so we're just trying to find the 0.
You're trying to find the 0 of the denominator polynomial. That's exactly right. 1?
Negative 1.
Negative 1. What's negative 1 squared? 1. So you got 2 of them, right? All right, so we have how many vertical asymptotes? 2. So what you're going to do is you're going to say, okay, you're going to say vertical asymptotes are at x equals 1, x equals negative 1.
Is that it?
Well, that answers part of the question. What are they asking us to also find?
Horizontal.
Horizontal. So this is where we have to let x get big. X has to go to positive infinity and negative infinity. Katie told me it's what? It's 2. Now why is it 2? Because look at the powers of x.
They're the same.
They're the same.
2.
So it's going to be 2. Very good. Does that make sense?
So what if the powers weren't the same?
Yeah.
Good question. Then it depends upon which power is bigger. Because the bigger power is the dominating power. Now if that dominating power is in the denominator, then that means the denominator will always dominate. It means it always gets bigger and bigger and bigger. And what happens in a fraction if the denominator gets bigger?
Smaller number.
The fraction gets smaller and smaller and smaller. So if the power of the denominator is larger than the power of the numerator, you can guarantee that your horizontal asymptote is what?
0.
0. But if the power of the numerator is greater than the power of the denominator, then that means the numerator is getting bigger and bigger and bigger and bigger. So now, Abby, it's either going to go to positive infinity or negative infinity, depending upon the leading coefficient.
So it would be positive.
In this case, if I had a 2x cubed over an x squared minus 1, it would be positive infinity. But if I had a negative 2x cubed over x squared minus 1, then it would be negative infinity in that case. B, where are the vertical asymptotes? How do we find the vertical asymptotes? What do we do? Set what equal to 0? Just the denominator, right? Because we're only looking for the excluded values of the denominator. Okay, so is that guy factorable?
No, yeah.
Yes, he's factorable. So what does he factor into?
-3, 1, 2.
X minus 3, x plus 2. X minus 3, x plus 2. So that means that the vertical asymptotes are where? At 3 and 2. But check this out, Sydney. The numerator also factors. It factors into x minus 1 times x plus 2. And look what? Do you see that you have an x plus 2 in common? This is called removable. And what that means, Abby, is that if x plus 2 is removable, that means that negative 2 is no longer a vertical asymptote. It's now just an excluded point. We still can't plug negative 2 into the function. But it's not going to blow up on us. What's going to happen is the graph is going to be an open hole at negative 2. But we still do have a vertical asymptote. Where is that?
3.
At 3. So x cannot be negative 2. Why? Because, Caitlin, if you go back to the original function, if you plug negative 2 in the original function, you're going to get 0 over 0. And that is not a real number. That's an undefined value. So you can't do that. You still can't plug in negative 2.
Would your answer be 3x cannot equal negative 2? Or
Okay. The answer would be this. The excluded values are 3 and negative 2. The vertical asymptote is x equals 3.
Okay.
In other words, x cannot equal 2. And this is a short way of saying cannot, the exclamation point.
Why is 3 excluded?
Why is what?
3 excluded?
3 is excluded because if I put 3 here into this function, I get 3 minus 1 over 3 minus 3. Uh-oh, that's a problem. But 2 is also excluded, Abby. Now check this out. 2 minus 1 is 1. 2 minus 3 is 1 over negative 1 is negative 1. Is that a real number? But Mr. P, I thought you told me that negative 2 was excluded. It is, because what happens if you put negative 2 in the original function? 0 over 0, right? So if you remove something, that only stops it from being a vertical asymptote. It doesn't stop it from being what? An excluded value. It's still excluded. You can't plug it into the function, but it at least stops it from being a vertical asymptote if you remove it. Okay? If you remove it, it's no longer going to explode to infinity, and that at least is nice. But you can't plug the number in, Joshua. Okay? Analyzing graphs of rational functions. Guidelines. Let a function be a numerator over a denominator where both are polynomials. Simplify the function if possible. Find and plot the y-intercepts, if you have any, by evaluating f of 0. And that makes sense, right? If you plug in x equals 0, you're finding where it hits the y-axis, right? 3, find the zeros of the numerator, if any, by solving the equation nx equals 0. Then plot the corresponding x-intercepts. So if the numerator is ever 0, Abby, you know you have x-intercepts. Find the zeros of the denominator, if any, by solving the equation d of x equals 0. Then sketch the corresponding vertical asymptotes. This answers your previous question, Sydney. How do we graph something like that?
Okay.
This is how we do it. And we have to get all of these steps, by the way, I'm going to show you that all of these steps are rather simple, but you've got to remember to do them. Okay? Number 5, find and sketch the horizontal asymptote, if any, by using the rule for finding the horizontal asymptote of a rational function. Number 6, plot at least one point between and one point beyond each x-intercept. So right now, I'm just reading. This isn't going to make sense until we actually do it. Number 7, use smooth curves to complete the graph between and beyond the vertical asymptotes. Okay, let's make this tangible. Let's make this something that we can actually do. Okay, step number 1. Step number 1 is this. Look at the numerator, look at the denominator. What is the numerator function? 3. If you set 3 equal to 0, is it ever possible for 3 to equal 0? No. This immediately means that this function has no x-intercepts. So it never hits the x-axis. Okay? Now look at the denominator. The denominator function is what? Are there any excluded values? 2. Is the x minus 2 removable? Meaning, can we find an x minus 2 in the numerator to get rid of it? No. So not only is 2 excluded, it's also a vertical asymptote. So we found a vertical asymptote. Now, let's find the y-intercept. Let's plug 0 into the function. What do I get when I plug 0 into the function? 3 over negative 2, which as a decimal is negative 1.5. There's my y-intercept. I know where it hits the y-axis. Do I have any horizontal asymptotes? The power of the denominator is what?
Greater.
What is the power of the denominator? It's 1. What's the power of the numerator? 0. It's a constant, right? So the power of the numerator is 0. Whenever you have a constant, it's 0. So the denominator is greater. Well, if the denominator power is greater, what does that say about the horizontal asymptote? It's 0. So now, do we have a vertical asymptote? Yeah. Do we have a horizontal asymptote? Do we have a y-intercept? Do we have any x-intercepts? No, we don't, but at least we know it doesn't hit the x-axis, right? Now we can plot everything that we do know about this and start plugging it in. So what we do first, Sydney, is we put a dashed line through 2, and that's the x-intercept, the vertical asymptote, excuse me. We put 0, negative 1.5, that's the y-intercept. And now as I approach 2 from the left, I know that the function is going to go down, 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 down.
How do you get that point over there?
This point right here, this is which step right here? Let's go back up to the guidelines. This is step number 6. Plot at least 1 point between and 1 point beyond each x-intercept. Well, we don't have any, right? So what they're doing now to find that point is they're plugging in x equals negative 2, and they're getting a y value. So yeah, plug something in. Get an ordered pair is what that does. When we did the transformations, what was the best way to do the transformations? Plotting ordered pairs, right? And then doing the transformations on the ordered pairs. Same idea. We're just plugging in an x value. What is it? Does it have to be negative 2? No, Abby could have chosen negative 3. What happens when we plug negative 3 into this function? 3 over negative 3 minus 2 is 3 over negative 5, which is negative 3/5, right? So that means that the ordered pair, negative 3, comma, negative 3/5 is an ordered pair on the graph, right? And that's all it does, is it gives us an ordered pair on the graph. And why is that useful? Because it helps us kind of figure out what it looks like. So that's why they graphed this point right here. Makes it kind of help us to figure out what it looks like, right? And how would we get an even better view or understanding about how the function looks? How could we get an even better understanding? More points, right? Keep plugging in more stuff. Ooh, I want to plug in 10. 3 over 10 minus 2 is 3/8, so I know that 10 comma 3/8 is a point on the graph. Now I'll plug in 5. 3 over 5 minus 2, well, 5 minus 2 is 3, 3 over 3 is 1, so I know that 5 comma 1 is a point on the graph, right? Does that make sense? So I know that my function now looks like this. There's the vertical asymptote, and those are the techniques to actually graphing the function. Okay? All right, let's look at this function right here. Step number 1, what's the numerator? 2x minus 1. Is there a place, what are the zeros of the numerator? Not 0.
Half.
1/2, right? What does that mean? What does that mean? What have we just found? We found the 0 of the numerator. That's equal to what? Not the horizontal. Not the vertical. The x-intercepts. That's the x-intercept. So where does it hit the x-axis? At 1/2. Now look at the denominator. What are the zeros of the denominator? 0. Is 0 removable? No. There's no common factor of x up at the top. So that means that 0 is excluded and it's a vertical asymptote. So now we have the vertical.
Is that the Y-intercept too?
Isn't it the y-intercept? Good question. How do we get the y-intercept? Plug in what? 0, but that's a problem. We can't do that, right? Why can't we plug in 0?
Because if you plug it in, it's undefined.
So what does that say about the y-intercept? There is none. It never hits the y-axis. Does that make sense? Does this have a horizontal asymptote?
Yes.
Yes. Where is it? 2, because the power of the numerator is 1, the power of the denominator is 1. They match, so it's the leading coefficient of 2. Now we're just going to plug in some points. So we're going to pick some random points now, Abby. So what happens when I plug 2 into this function? 2 times 2 is? Minus 1 is? Over? Which is? 3/2, right? I gotcha, because I do that all the time. 3/2, which is the same as 1.5, right? Okay, that gave us an ordered pair, right? Why are ordered pairs useful? They help us. They help us graph it. Help us figure it out. Let's plug in another one. Pick a negative number. -2. 2 times -2. -4 minus 1 over -2. -5 over -2 is positive 5/2, right? Or 2.5, right? Now we have another ordered pair. Where is it?
Is it negative?
Negative.
No,
No, it's a negative over negative. Where's the ordered pair now? -2, comma 2.5. Now we have another ordered pair. So what they do is they start to plot it all out. Check this out. Horizontal asymptote here at 2. They chose to plug in -1. They got 3, right? Vertical asymptote at 0. And right there, there's the 1/2, right? 1/2 is where the numerator is equal to 0. That's where it hits the x-axis right there. Does that make sense? Okay, let's see here. I'm not expecting perfect understanding today, maybe about 40%, 50%. Let's go to the homework real quick, and let's look at...
We looked at number Thursday?
Like the 5 through 8 section.
5 through 8?
Yeah.
Okay. So, okay, now let's see what it's asking us to do. Complete each table for the function. Determine the vertical and horizontal asymptotes of the graph of the function. Then C, find the domain of the function. So for part 5, what is the excluded value? Positive 1. So the domain is all real numbers except 1. The table is going to help us look at what the points are. First we start at 0.5, then we go to 0.9. Then 0.99, 0.999. What are we approaching?
0.
Nope, 1. We're approaching the excluded value, right? Now, which direction are we approaching that excluded value? From the left, right? So we're approaching from the left. We just want to figure out what the function does as we approach from the left. So first what you do, Abby, is you plug in 0.5. 1 over 0.5 minus 1. 1 over -1/2, which is -2. Then when you go all the way to 0.999, Caitlin, you're going to get something that's really negative. So what's happening here is the function's going towards negative infinity.
Why, do you have to plug it into like all three of those tables, or just like one for each one?
No. You're approaching 1, so yes, you're going to plug them all three tables for 5, 6, 7, and 8. Okay? Because look at this one right here. The middle table, we're approaching what? 1 again, but from which direction? From the right. And what you're going to see is you're going to see the function is going to explode to positive infinity as you do the calculations and you put in the numbers. And then what are we letting x approach here in this table? Infinity. And you're going to see the function get smaller and smaller and smaller, closer to 0 as you plug that in. The vertical asymptote for this function is what? For number 5? Is 1. What's the vertical asymptote for number 6? 1 again. What's the horizontal asymptote for number 6?
Oh, wait. What you said, vertical?
What's the vertical asymptote for number 6? We said it was 1. What's the horizontal asymptote? 5, because the powers match. They're the same. And what's going to happen, Kate, is that as you let x go to infinity, as you plug in numbers that are bigger and bigger and bigger, you're going to see the ratios here turn out to be closer and closer to 5. That's what you're going to see numerically. So the reason why this question is given is because they want you to see numerically what you already see visually. Because sometimes you don't have the picture, right? So you have to have the numbers in order to figure out what the picture is going to look like. This one, number 7, has 2 vertical asymptotes. What are they? Negative 1 and 1. So the domain of this function is all real numbers except 1 and negative 1. All right, that should get you started. God bless you. Have a good day.